Imagine a mosaic made of millions of tiny colored tiles. A digital camera works the same way. It captures light and turns it into a flat grid of little squares called pixels, short for picture elements. A self-driving car doesn't have. Here's the big problem. A photo is flat, but the real world has depth. Look at a tree. In the image it's just a blob of green pixels. But is it 5 meters away or 50? A car must know the real. To understand the puzzle, let's build a simple camera. Light bounces off a tree in all directions. If we put a tiny pinhole in a box, only one thin ray from each point on the tree can squeeze through. That ray travels. Let's solve a real self-driving car problem. The camera sees a car ahead. In the image, the car is 50 pixels tall. We know from the real world that a typical sedan is about 1.5 meters tall. The camera's focal length. Here's how to master this. The most common mistake is using pixel counts directly in the formula. You must first convert pixels to a real sensor size using the camera's specs. A powerful trick, if you know the real size of. Imagine a completely dark room with just one tiny hole in a wall. Light from outside squeezes through that hole and paints a picture on the opposite wall, but it's flipped upside down. That's a pinhole camera, the simplest camera possible, with no. Every camera, from your phone to a cinema rig, is built on this simple idea. Understanding the pinhole model explains why images are upside down inside a camera and how a sensor captures them. It's the mental model that makes lenses and focal length make. Light bounces off an object and travels in straight lines in all directions. Only the rays aimed exactly at the pinhole get through. Because the hole is so small, a ray from the top of the object must angle downward to pass. Let's put a 2-meter tree 4 meters in front of our pinhole camera. The camera's focal length, the distance from the pinhole to the sensor, is 10 centimeters. Because the rays form similar triangles, the image height is the object height times the focal. The most common mistake is drawing the image right side up. Always remember the rays cross. A quick trick, sketch just 2 rays from the top and bottom of the object through the pinhole, where they land on the image plane. An angle is simply a measure of how much you turn. Imagine standing still and spinning to face a different direction. The amount you spin is the angle. We measure it in degrees, where a full spin is 360 degrees. Angles answer a real question: how wide is your view? A camera doesn't see everything, it captures a slice of the world. This slice is called the field of view, and it's just an angle. A wider angle sees more, like opening A. We build angles from a full turn. Imagine a circle around you. A degree is just one slice of that circle, 1/360th of a turn. In our pinhole camera, the angle opens from the pinhole to the edges of the sensor. A bigger. Let's solve a real problem. A full-frame camera has a sensor 36 mm wide. With a 50 mm focal length, the half width is 18 mm. The angle from center to edge is arctan, 18/50ths, about 20 degrees. Doubling gives the full field of view, roughly 40. A triangle is the simplest closed shape you can make with straight lines. It has 3 sides and 3 corners, which we call vertices. Think of it as the shape that connects any 3 points in the world. In your pinhole camera, every point you see forms a triangle. One corner is the real-world point, one is the pinhole, and one is its image on the sensor. Understanding this triangle is the key to how cameras capture our 3D world. Light from a point in the world travels in a straight line to the pinhole, then continues straight to the sensor. These 2 light paths form 2 sides of a triangle. The third side is the imaginary line connecting the world point. Imagine a 3-meter tree, 6 meters from your pinhole camera with a 2 centimeter focal length. The world tree pinhole triangle and the image tree pinhole triangle are similar. So, image height over focal length equals tree height over distance. That's 0.02 times 3 divided by 6. For any camera problem, first find the 3 points, world, pinhole, image. The biggest mistake is mixing units like meters and centimeters. Convert everything first. A great trick is to always sketch the triangle. Today, try this: use a lamp to cast a. Imagine you take a photo of a tree and then print it twice as big. The tree looks exactly the same, just larger. That similarity, two triangles with the same 3 angles, but their sides are multiplied by a scale factor. You can't always measure a tall building with a ruler. But if you can make a tiny triangle similar to the big one, like the one formed inside your pinhole camera, you can use a simple proportion. The camera's image triangle is a miniature. If 2 triangles have the same angles, their sides must be in the same proportion. Think of it like a recipe: if you double one side, you must double all the others to keep the angles. In our camera, the world triangle. A 10-meter tree is 20 meters from your pinhole camera. The camera's focal length is 0.05 meters. The image of the tree on the sensor is 0.025 meters tall. We can check this: the world triangle has height 10 and base 20. The most common mistake is mixing up which side corresponds to which. Always pair the side opposite the same angle. A quick trick: write the proportion as a fraction, and make sure the units cancel out. Try it yourself. Measure a lamp. Imagine a right triangle. Sine, cosine, and tangent are just 3 special fractions you can make from its sides. Each fraction pairs a different 2 sides and is tied to one of the triangle's sharp angles. They are like a secret code. In our pinhole camera, we have similar triangles but often know only one side and an angle. We need a rule that says, if I know this angle and this side, the other side must be this many times bigger. That rule. Look at a right triangle. Pick an angle. The side across from it is opposite, the side touching it is adjacent, and the long side is a hypotenuse. Sine is the fraction opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite. Your camera is 10 meters from a tree. The angle from the lens to the treetop is 30 degrees. Which ratio links the tree's height, opposite, to your distance, adjacent? Tangent. So height equals distance times tan of the angle. Tan 30. Always label the 3 sides before picking a ratio. The most common mistake is using the hypotenuse when you need the adjacent side. Remember the chants SOHCAHTOA: sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite. Imagine you see a friend in a photo. You know their real height, and you can measure how tall they appear on the image. The tangent trick is a simple formula that uses these 2 numbers, plus the camera's focal length, 2. We often need to know how far away something is, like a robot avoiding a wall, or an augmented reality game placing a character on your table. Using 2 cameras or a laser is expensive. This trick solves the problem with just 1. Picture the camera's pinhole. The real object and its tiny image on the sensor form 2 similar triangles that share the same vertex at the pinhole. The tangent of the angle at the pinhole is the opposite side, real height, over the. Let's find how far you are from a standard 2-meter tall doorway. Your camera has a 20 mm focal length. In the photo, the doorway appears 4 mm tall on the sensor. Plug in, distance equals 2 meters times 20 mm, divided by. Always check that real height and image height are in the same units, like both in millimeters. The most common mistake is putting image height on top instead of real height. Remember, the bigger object goes with the bigger distance. A handy trick. A single camera only measures the angle an object takes up. It can't tell if that angle comes from a small thing nearby or a huge thing far away. Both produce the exact same image on the sensor. Imagine a self-driving car seeing a stop sign. Is it a real sign 20 meters ahead, or a tiny toy sign right in front of the lens? A single camera can't know, and guessing wrong could be a disaster. This is From our earlier tangent trick, we know tan theta equals the object's real height over its distance. But with one camera, we only measure the angle theta. That leaves us with one equation and two unknowns, real height and real distance. Infinitely many. You take a photo of a door. On the sensor, its image is 2 millimeters tall, and your focal length is 4 millimeters. Using similar triangles, the angle is 30 degrees. The tangent of 30 degrees is about 0.58. So, 0.58 equals the doors. The classic mistake is to assume an object's real size to calculate distance, which is just a guess. A clever trick is to look for a reference object of known size in the same scene. Right now, close one eye and try. Stereo vision means using two cameras, just like your two eyes. When you look at something, each eye sees a slightly different picture. Disparity is the sideways shift of an object between the left and right images. Hold your thumb close and remember, one camera alone can't tell if something is small and near or big and far. That's the ambiguity we saw with monocular vision. Stereo vision breaks that confusion. By comparing the two views, we get a direct, geometric measurement of. Imagine two pinhole cameras side by side, separated by a baseline, like your eyes. An object projects onto each image plane. The horizontal shift, or disparity, between these two projections creates a triangle with the baseline. Using similar triangles, just like a robot with two cameras 10 centimeters apart sees a cup. Its focal length is 500 pixels. The cup center is at pixel 200 in the left image and pixel 250 in the right. The disparity is 250 minus 200, which is. The trickiest part is finding the exact same point in both images. A tiny mismatch ruins the measurement. Always remember, a bigger disparity means a closer object. When you calculate, make sure the pixel units cancel, leaving a real distance. Try. Imagine two eyes looking at a point. The line connecting them is the baseline. This baseline and the lines of sight to the object form a triangle. That triangle is the key to finding depth. A single camera can't tell if an object is small and near or large and far. With two cameras, the object's position forms a unique triangle. The baseline is the triangle's base, and its shape reveals true distance. We use similar triangles. One triangle is formed by the object and the two cameras. The other is formed by the image points on the sensors. The ratio of depth to baseline equals the ratio of focal length to disparity. Rearranging gives. Let's measure a toy 25 centimeters away. Our cameras are 10 centimeters apart, with a 5 millimeters focal length. The toy shifts 2 millimeters between images. Using the formula, depth equals 10 centimeters times 5 millimeters, divided by 2 millimeters. That's 25. A wider baseline gives better depth resolution. The most common mistake is mixing units. Keep them all in millimeters. Remember, disparity is only horizontal. Try it now. Hold a finger up and blink one eye at a time. The shift you see is Imagine taking a photo, but instead of color, every dot records how far away that spot is. That grid of distances is a depth map. It's like a top-down weather map, but for distance, bright spots are close, dark spots are far away. A single photo is flat, you can't tell if a blob is a close cat or a faraway car. A depth map solves this by giving every pixel a distance. For a self-driving car, this turns the camera view into a 3D understanding. We already know how two cameras find distance for one point using disparity and triangulation. To build a depth map, we just do that for every single pixel. The left and right images are compared, and the shift, the disparity, is found for each. A car's two cameras are 0.3 meters apart. The focal length of each camera is 800 pixels. For one pixel, the matching algorithm finds it shifted by 4 pixels between the left and right images. Using our triangulation formula, depth equals baseline. The most common slip-up is thinking disparity is the same as depth. They're opposites. A large disparity means the object is very close. A tiny disparity means it's far away. To feel this, hold a finger close to your nose and alternate. A self-driving car builds a live 3D map of everything around it: cars, people, curbs. Think of it as an invisible safety bubble that constantly asks, how far is that thing, and how fast are we closing in? It fuses the dense color. Knowing depth isn't just about seeing, it's about surviving. The car must spot a child running onto the road and brake in time. It calculates the time to collision by tracking how quickly an object grows bigger in the image, using the same similar triangle. The car starts with a stereo depth map from two cameras, using disparity and triangulation. But cameras struggle in the dark or with plain white walls. So it fuses this with LiDAR, which fires laser pulses to measure exact distances, creating a. Imagine a parked car 50 meters ahead. The stereo cameras, using a 0.3 meter baseline and a disparity of 4 pixels, estimate the distance at 48 meters. The LiDAR pings it at 50.1 meters. The car's computer knows LiDAR is more reliable at. A common mistake is trusting one sensor blindly. Cameras fail in fog, LiDAR fails on glass. The trick is redundancy, always fuse. A quick problem-solving trick: you can estimate time to collision just by how fast an object expands in the image, no distance needed. Imagine you're a self-driving car. Your whole job is to turn flat camera images into a 3D map of the world. This journey starts with a simple pinhole, uses triangles and trig ratios, and finally combines two views to create a point. A car needs to know if that blob is a faraway truck or a close-by toy. One camera sees a direction but can't tell size from distance. That's the ambiguity problem. By using two cameras, like our two eyes, the car can measure. It's a chain reaction. The pinhole makes a tiny, upside-down image, forming similar triangles between the world and the sensor. For one camera, we use the tangent ratio to find an angle to the object. With two cameras are known a baseline apart. Let's solve a real problem. A self-driving car's two cameras are 0.2 meters apart. A pedestrian creates a disparity of 50 pixels on the sensor, and our camera's focal length is 800 pixels. We plug these into our depth formula, depth equals. The most common mistake is mixing units. Keep baseline and depth in meters, and focal length and disparity in pixels. A handy trick: disparity is always measured in pixels on the image sensor, never in real-world units. To make this stick, try it.